Look at the room you are in. The walls, the floor, the air itself. Everything you see is held together by rules. The electrons in your body orbit their atoms at specific distances. Light moves at a fixed speed. Gravity pulls with a strength that never changes. These rules feel permanent. They feel like the way things have to be. But here is something physicists have known for decades and rarely discuss in public. The rules might be temporary, not temporary on human timescales, temporary in a deeper sense. The laws of physics as we experience them may be an accident of energy, and accidents can be corrected. Somewhere in the universe right now there may be a bubble. It is not made of anything you could touch or see. It is a region where the rules are different, where electrons do not orbit, where light does not travel, where matter as we know it cannot exist. And this bubble is expanding. It moves at the speed of light, which means it sends no warning ahead of itself, no flash, no sound, no gravitational ripple, nothing. The first sign of its arrival would be the moment it reached you, and that moment would also be the last moment of everything you have ever known. This is not science fiction. This is a prediction that emerges directly from our best-tested theories of particle physics. It has a name. Physicists call it false vacuum decay. Stephen Hawking wrote about it. The team that built the Large Hadron Collider calculated the odds before they turned the machine on, and the conclusion they reached was not comforting. Our universe, according to the standard model of physics, appears to be sitting on a knife's edge, a metastable state, a configuration of energy that looks stable but is not, a false floor above a deeper basement. Tonight we're going to descend into that basement. We're going to understand exactly what the false vacuum means, why physicists believe we might be living inside one, and what would happen if we were not. This is not a video about unlikely scenarios. This is a video about the actual structure of reality and a flaw that may be built into its foundations. If this kind of slow, careful journey into the strangest territory of physics is something you value, consider tapping the like button. It helps more than you might think, and subscribe if you want more nights like this one. Now let us begin. The first thing you need to understand is what physicists mean when they use the word vacuum. In everyday language, a vacuum is empty space. The inside of a sealed container with all the air pumped out. The void between stars. Nothing there. But in physics, the word means something more precise and far stranger. A vacuum is not the absence of stuff. A vacuum is the lowest energy state of a system. It is what remains when you have removed everything that can be removed. Think of it this way. Imagine you have a bowl, a physical bowl sitting on your kitchen counter. You can put things in the bowl. Marbles, water, sand. Each time you add something, the bowl has more stuff in it. A vacuum, in the everyday sense, would be the empty bowl. Nothing inside. But now imagine the bowl itself has a bottom that can move. It can sit at different heights. The empty bowl with its bottom at the floor is different from the empty bowl with its bottom somehow suspended 3 feet in the air. Both bowls are empty, but one is in a lower position than the other. One has less potential energy, and if you removed whatever was holding the floating bowl's bottom in place, it would fall. The vacuum of physics is not about whether the bowl has marbles. It is about where the bottom of the bowl sits. The true vacuum is the lowest possible position, the configuration where there is no more potential energy to release. And here is the disturbing part. We do not know if our universe's bottom is at the floor. We do not know if we are in the true vacuum. We might be in the floating bowl. And if we are, the bottom could fall at any moment. Let me try once more to give you a feel for this. Imagine a ball resting in a valley. The ball is stable. If you push it a little, it rolls back to the centre. This is what physicists call a stable equilibrium, the lowest point. Now imagine the valley has a shape you did not notice at first. There is a small dip where the ball sits, yes. But beyond a ridge to one side, there is a much deeper valley. The ball looks stable. It acts stable. If you nudge it gently, it returns to its little dip. But if something were to push it hard enough to crest that ridge, it would roll down into the deeper valley and never come back. The small dip is the false vacuum. The deeper valley is the true vacuum. And our universe may be the ball. Stop and feel the weight of that for a moment. Everything you see around you, everything you have ever experienced, every atom in your body, and every photon that has ever touched your eyes, all of it exists because the universe is sitting in a particular configuration of energy. If that configuration is not the lowest one, If there is a deeper valley somewhere in the landscape of possibility, then everything we call reality is a temporary arrangement, a metastable state waiting to decay. To understand how physicists arrived at this unsettling conclusion, you need to understand something about the Higgs field. You have probably heard of the Higgs boson, the particle discovered at the Large Hadron Collider in 2012, the so-called God particle, a name physicists tend to dislike because it oversells the metaphysics and undersells the physics. But the Higgs boson is not the important part. The boson is just a ripple. What matters is the field. The Higgs field is not like the fields you might picture from everyday experience. It is not a magnetic field pulling on metal. It is not a gravitational field pulling you toward the Earth. The Higgs field is something more fundamental. It pervades all of space. Every cubic centimetre of the universe is filled with it. And it has a property that makes it unique among the fields we know. It has a non-zero value even in what we call empty space. Most fields, when nothing is happening, settle to zero. The electromagnetic field in deep space, far from any charges, is zero. Ripple it and you get light. But at rest, zero. The Higgs field is different. At rest, in the vacuum state, it has a non-zero value. It fills space with a kind of constant background presence, and this background presence is what gives particles their mass. This probably sounds abstract, so let me give you a picture. Imagine space as a vast ocean. Not water, but something more fundamental, a medium that everything must travel through. Some particles move through this medium easily, barely noticing it. These are the light particles. The photon, for instance, does not interact with the Higgs field at all, which is why it is massless and travels at the speed of light. Other particles interact strongly with this medium. They feel drag. They resist acceleration. They have mass. The electron has a small mass because it interacts weakly with the Higgs field. The top quark has an enormous mass because it interacts very strongly. Mass in this picture is not a thing particles have. Mass is a relationship particles have with the Higgs field. Now here is where the vacuum enters. The value of the Higgs field, the height of that background presence filling all of space, is what determines the masses of all the particles. Change the value of the Higgs field and you change the masses. Make it zero, and the electron becomes massless. It would zip through space at the speed of light, unable to form atoms, unable to make chemistry, unable to build you. And here is the question physicists have been asking since the 1970s. Why does the Higgs field have the value it has? Why this particular height and not some other? The answer has to do with energy. The Higgs field, like any field, has a potential energy associated with its value. You can draw this as a curve. On the horizontal axis, the value of the field. On the vertical axis, the energy. And the shape of that curve determines everything. If the curve looks like a simple bowl, curving smoothly down to a single lowest point, then the field naturally settles there. One stable minimum, one vacuum. End of story. But the curve for the Higgs field does not look like a simple bowl. The standard model predicts a more complicated shape. It has the classic Mexican hat profile, a shape that looks like the brim of a sombrero, a bump in the middle where the field value is zero, and a trough around the rim where the field settles to its non-zero value. The universe rolled down from that central bump during the Big Bang and came to rest in the trough. That is why the Higgs field has its current value. That is why particles have the masses they have. But there is a twist, and the twist only became clear once we knew the mass of the Higgs boson itself. In July of 2012, physicists at CERN announced they had found the Higgs boson. The discovery was the culmination of decades of searching, billions of dollars of investment, and the construction of the most complex machine humans have ever built. The Large Hadron Collider is a ring 27 kilometers in circumference, buried 100 meters beneath the Swiss-French border. It accelerates protons to 99.999991% of the speed of light, and smashes them together millions of times per second. The detectors that surround those collision points are the size of cathedrals, and all of it, every magnet and every sensor and every line of code, was designed to answer one question. Does the Higgs boson exist, and if so, how heavy is it? The answer came back. The Higgs boson exists. Its mass is 125 GeV, 125 billion electron volts, about 133 times the mass of a proton, and that number, that specific number, turned out to be the most disturbing possible result. Let me explain why. The mass of the Higgs boson is related to the shape of the potential energy curve. A heavier Higgs would mean a steeper curve, a deeper trough, a more stable vacuum. A lighter Higgs would mean a shallower curve, a gentler trough, a vacuum that might not be stable at all. And when physicists plugged the measured value into their equations, they found something unsettling. 125 GeV is right on the edge. If the Higgs were just a bit heavier, maybe 130 or 140 GeV, the vacuum would be unambiguously stable. The trough we sit in would be the deepest point on the curve. No lower valley would exist. We would be safe. If the Higgs were much lighter, maybe 110 or 100 GeV, the vacuum would be unambiguously unstable. The trough would not even be a trough. The ball would have no place to rest. The universe would have already collapsed. But 125 GeV is right in the middle, right on the knife edge. At that mass, the calculations show something intermediate. The trough we occupy is a local minimum but not a global minimum. There is a lower valley, but the ridge between us and that valley is high enough that quantum mechanics alone will not easily push us over. We are metastable. We are the ball in the false vacuum, sitting in our little dip, unaware of the deeper valley beyond the ridge. Say that slowly. Our universe is metastable. This is not a fringe idea. This is not speculation dressed in equations. This is the mainstream, consensus, boring prediction of the standard model of particle physics when you plug in the measured values of the Higgs mass and the top quark mass. The calculation was done independently by multiple research groups in the years following the Higgs discovery. It was confirmed and refined as the measurements improved, and the answer has not changed. The universe, as best we can tell, is not in its ground state. It is in a false vacuum. Now let us ask the question you're already thinking. What happens if the false vacuum decays? The answer involves quantum mechanics and a process called quantum tunneling. In classical physics, if a ball is sitting in a valley and there is a ridge in the way, the ball stays put unless something gives it enough energy to climb over the ridge. Push it hard enough, and it crests the ridge and rolls down the other side. Push it too softly and it just rolls back. Quantum mechanics is different. In quantum mechanics, particles do not have definite positions. They are spread out into probability distributions. And this means that even if a ball does not have enough energy to climb the ridge, there is a small probability that it will simply appear on the other side. It tunnels through the barrier rather than climbing over it. For individual particles, this effect is well tested and routine. Radioactive decay, for instance, is quantum tunneling. The particle inside the nucleus does not have enough energy to escape, but it tunnels out anyway. That is why atoms decay. The false vacuum can tunnel in the same way. Somewhere in space, at some random point, the Higgs field could tunnel from its current value to the lower value of the true vacuum. It would not need an outside push. It would not need a collision or a cosmic ray or a black hole. It would happen spontaneously, randomly, as a quantum fluctuation, and when it happened, a tiny bubble of true vacuum would nucleate. Inside that bubble, the Higgs field would have a different value, a lower energy value, and because the masses of all particles depend on the Higgs field, the masses of all particles inside the bubble would be different. The electron would not have the same mass, the proton might not be stable, chemistry as we know it would be impossible. The bubble would not contain anything you would recognize as matter. And here is the part that matters. The bubble wall would expand. Picture this carefully. The bubble starts small, perhaps the size of an atom, perhaps the size of a proton. It nucleates at some random point in space, and then the wall begins to move outward. Inside the bubble is the true vacuum, lower in energy. Outside the bubble is the false vacuum, higher in energy. The wall is the transition region where the Higgs field is changing value. And because the energy inside is lower than the energy outside, the wall accelerates outward. It gains speed. It picks up energy from the difference in vacuum states and uses that energy to go faster. The physics predicts that the wall accelerates until it reaches the speed of light. Let that settle for a moment. The wall moves at the speed of light. Nothing can outrun it. Nothing can send a warning ahead of it. Light itself travels at the same speed, so the first photon from the bubble's edge would arrive at the same instant as the wall itself. You would have no time between seeing it and being inside it. Not a microsecond, not a nanosecond, not a Planck time. The arrival of the bubble and the end of everything you know would be the same moment. I want you to picture what this would look like if it happened. You're sitting in your room. It is a Tuesday evening. You're watching this video, perhaps, or doing something else entirely. The universe beyond your walls is quiet. Stars burn in their distant orbits. Galaxies spin in their slow rotations. Nothing seems unusual. And then, somewhere, a bubble nucleates. Perhaps it is in the intergalactic void, a billion light years away. Perhaps it is closer. Perhaps it is at the edge of the Milky Way. Perhaps it is in the next solar system. Perhaps it happened 5 minutes ago and the wall is already on its way. You would not know. There is no way to know. The bubble could have formed a billion years ago at the other end of the universe and be racing toward us right now at the speed of light, and we would have no indication. We would have no instrument capable of detecting it. We would have no theory capable of predicting where or when it might appear. We would simply continue living until the wall arrived, and then, in less than the time it takes a photon to cross a single atom, everything would change. The Higgs field beneath your feet would shift to its new value. The electrons in your body would have new masses. The bonds holding your molecules together would become impossible. You would not experience pain. You would not experience anything. Experience requires neurons, and neurons require chemistry, and chemistry requires the Higgs field to have its current value. The wall would not kill you in any conventional sense. It would simply make the concept of you incoherent. This is not how it would feel. There would be no feeling. This is how it would fail to feel. The transition from existence to non-existence would be faster than any process capable of registering a transition. The wall does not destroy you. It erases the category of things that can be destroyed. Now I need to address the obvious question. How likely is this? The honest answer is that we do not know. The calculations are delicate. They depend on the exact values of the Higgs mass and the top quark mass, and those measurements have uncertainties. They also depend on whether the standard model is exactly correct at very high energies, and we have strong reasons to suspect it is not. New physics, undiscovered particles, might change the shape of the potential. They might raise the ridge and make the vacuum more stable, or lower it and make the vacuum less stable. We are operating at the edge of our knowledge, but let me give you the numbers physicists have calculated under the assumption that the standard model is exactly correct. The probability of a bubble nucleating in our observable universe is unimaginably small. The half-life of the false vacuum, the time you would have to wait for a 50% chance of decay, is estimated at something like 10 to the power of 10 to the power of 100 years, a number so large that writing it out would require more digits than there are particles in the universe. On human timescales, on even cosmological timescales, the odds of a spontaneous vacuum decay are effectively zero. But there is a complication. That calculation assumes the universe is undisturbed. It assumes the Higgs field starts in its current state and stays there unless quantum mechanics randomly pushes it over the ridge. And while that random push is unimaginably unlikely, there are other ways to push. High-energy events can push. A collision energetic enough might kick the Higgs field over the barrier locally. Not a random quantum fluctuation, but a deliberate shove. And when physicists started planning the Large Hadron Collider, they asked themselves a question. Could the LHC produce collisions energetic enough to trigger vacuum decay? The answer, after careful calculation, was no. The energies at the LHC are enormous by human standards, but they are tiny compared to the energies of cosmic rays that have been striking the Earth for billions of years. If LHC-scale energies could trigger vacuum decay, the cosmic rays would have done it long ago. The fact that we exist is proof that those energies are safe. But here is the thing. The cosmic ray argument only tells you that energies up to a certain point are safe. It does not tell you that all energies are safe. Somewhere above that threshold the energies get dangerous, and we do not know where that threshold is. Stop and consider this for a moment. Our best theory of particle physics predicts that the universe is metastable, that we sit in a false vacuum, that the true vacuum, if it exists, would expand at light speed and be undetectable until it arrived, that there is no possible warning, no possible defense, no possible escape. The calculations suggest the spontaneous decay rate is fantastically low, but the calculations are delicate and depend on assumptions we cannot fully verify. This is not a failure of imagination. This is the structure of reality as disclosed by equations that make successful predictions every day. The same equations that predicted the Higgs boson before we found it. The same equations that calculate the properties of electrons to 12 decimal places. The same equations that let us build the transistors in your phone. When those equations are extended to their logical conclusions, they whisper something unsettling. The ground beneath our feet might not be the bottom. Stephen Hawking, in his final years, wrote about false vacuum decay. He called it the ultimate ecological catastrophe. He noted that in the true vacuum, the constants of nature would be different, chemistry would be impossible, and life as we know it could not exist. He did not write this to frighten. He wrote it because it was true, and because Hawking believed the public deserved to know what physicists actually thought about the universe they inhabited. And here is the part that transforms mere scientific speculation into something that keeps certain physicists awake at night. The bubble might already exist. Picture the universe as a vast ocean. Light takes time to travel across it. When you look at a star 100 light-years away, you are seeing it as it was 100 years ago. When you look at a galaxy 1 billion light-years away, you are seeing it as it was 1 billion years ago. The universe we observe is not the universe as it is. It is the universe as it was, at various points in the past, with the most distant parts being the most ancient. Now imagine that a vacuum decay event occurred 1 billion years ago in a galaxy 1 billion light-years away. The bubble would have nucleated and begun expanding at light speed. Right now, today, that bubble would be almost upon us. It would have swallowed billions of galaxies in the interim, stars, planets, civilizations if they existed, all erased, and we would have no idea. The light from the galaxies being destroyed would be overtaken by the wall. The warning, if there was one, would arrive at the same instant as the destruction. For all we know, the bubble is out there, growing, approaching, its leading edge invisible, defined by the fact that nothing escapes fast enough to announce its coming. This is the cosmological horror that distinguishes false vacuum decay from other existential risks. Asteroid impacts give warning. Supernovae give warning. Even gamma-ray bursts give warning, if only by milliseconds. Vacuum decay gives nothing. It is not a threat from outside the universe. It is a flaw in the architecture of the universe itself, a defect in the foundation that could manifest anywhere, at any time, without cause and without announcement. And the most disturbing part is that this is boring physics. This is textbook physics. This is what you get when you take the standard model seriously and run the numbers. The horror does not come from exotic speculation. The horror comes from the familiar equations applied correctly. Now let me turn to another question. Why does this happen? Why does the universe have this flaw built in? The answer has to do with the shape of energy landscapes. In physics, systems tend to seek their lowest energy states. A ball rolls downhill. Heat flows from hot to cold. Chemical reactions favour lower energy products. This is the second law of thermodynamics in action, the universe slouching toward equilibrium. But getting to the lowest state takes time, and sometimes systems get stuck in intermediate states. A ball can rest in a small valley without realising there is a deeper valley over the next ridge. Water can remain liquid below its freezing point if it is very pure and still. These metastable states can last for a long time, but they are not truly stable. They are waiting for a fluctuation large enough to push them over the barrier. The false vacuum is a metastable state of the Higgs field. The Big Bang left the field in a local minimum, not the global minimum, and that local minimum is where we have stayed for 13.8 billion years. But the deeper valley exists. The true vacuum is there, waiting. And the only question is when and where the first fluctuation large enough to create a bubble will occur. Why did the Big Bang leave us in a false vacuum? This is one of the open questions. Some physicists suggest it was random, a cosmic accident. Others suggest the dynamics of inflation, the rapid expansion in the universe's first moments, could have pushed the Higgs field into its current state. Still others suggest we should not be surprised, because if the universe were in the true vacuum, conditions might be incompatible with life, and we would not be here to ask the question. This last argument, a version of the anthropic principle, is slippery. It explains why we observe a certain kind of universe, but it does not explain why that kind of universe exists. It is a selection effect, not a cause. And it offers no comfort because even if we must be in a metastable universe to exist at all, that metastability eventually ends. I want to return to the physical picture because it is important to grasp this concretely. The Higgs field fills all of space. Every point in the universe is assigned a value of this field. Right now, everywhere we can see, the value is stable at its local minimum. The same value here as in the Andromeda galaxy, the same value in the Virgo cluster, the same value at the edge of the observable universe. But this uniformity is not guaranteed. The field has quantum fluctuations. At every point, constantly, the value jiggles slightly up and down. These fluctuations are tiny, far too small to push the field over the barrier under normal circumstances. But quantum mechanics deals in probabilities, and even vanishingly small probabilities are not zero. Somewhere, sometime, a fluctuation large enough to crest the ridge could occur. When it does, a small region of space would find itself on the downhill slope toward the true vacuum. The field in that region would roll down, gaining energy, accelerating. The boundary between the rolling region and the stable region would sharpen into a wall, and that wall would begin its light-speed expansion. Once started, the process cannot be stopped. There is no force that can hold back the wall. There is no technology that can reinforce the false vacuum. The energy difference between the states is built into the fundamental constants. It is not a problem to be solved. It is a feature of reality. Picture the night sky. The stars you see are islands of light in an ocean of darkness. But even that metaphor is too comforting, because in an ocean, the islands are made of stable land. What the false vacuum picture tells us is different. The islands are not land. The islands are ice. The ocean beneath them is warmer water, and at any moment a current of warm water could reach up and begin melting the ice from below. You would not see the melting starting. The first contact of warm water and ice would happen beneath the surface. By the time you noticed anything, by the time the island began to shift, it would already be too late. The structural integrity that held the island together would be compromised. What looked like permanent land would reveal itself as frozen water, as a temporary state, as something that had always been on its way to dissolution. The stars are ice. The galaxies are ice. Chemistry, biology, thought itself, all of it rests on the frozen surface of the Higgs field. And beneath that surface, the warmer water of the true vacuum waits. This is the nature of our situation. This is what the equations say. And there is something almost beautiful in it, in a terrible way. The universe is not permanent. The laws are not fixed. Everything we see, everything we know, everything we are is a temporary configuration, a shape that energy takes for a while before taking another shape, a story the cosmos tells itself before moving on to a different story. Now, before we go further, I need to be clear about something. The fact that false vacuum decay is possible does not mean it is imminent. The calculations, as I said, suggest an unimaginably long half-life under normal conditions. The universe could persist in its metastable state for longer than we can meaningfully comprehend. Trillions of years. Trillions of trillions of years. Timescales that make the current age of the universe, 13.8 billion years, look like a single heartbeat. But there is a difference between improbable and impossible, and there are factors that could change the odds. High-energy physics experiments, if they ever reach sufficient energy, could trigger local decay. Cosmological events, like the collision of black holes at velocities approaching a significant fraction of light speed, might release enough energy in a concentrated region to trigger nucleation. We do not know where all the thresholds are, and here is the part that haunts certain physicists. In an infinite universe, everything that can happen does happen somewhere. If the universe is truly infinite in extent, then somewhere, right now, vacuum decay is occurring. Somewhere the bubble is forming. Somewhere the wall is expanding. The only question is whether that somewhere is close enough that the wall will reach us before the universe ends for other reasons. In a finite universe, we might be safe. The probability per unit volume per unit time is so small that if the universe is finite, perhaps no bubble will ever form. We might persist in our metastable state until proton decay or heat death claims us in the unimaginably distant future. But we do not know if the universe is finite. We do not know how far it extends beyond what we can see, and that uncertainty is part of the shadow. This, then, is the landscape of the false vacuum, a universe that looks stable, but might not be, a ground state that might not be a ground state, a configuration of energy that could shift without warning, propagating outward at light speed, rewriting the rules as it goes. The theory is not speculative. It is the prediction of our best-tested framework. The uncertainty is not whether the physics is correct, but whether additional physics, undiscovered physics, saves us from the implication. And as we continue, we will explore that possibility. We will look at what it would take for new physics to change the picture. We will examine the measurements, the experiments, the margins of error. We will consider what it means for beings like us to live in a universe with this structure, and we will sit with the question that false vacuum decay forces us to ask. What does it mean to build a civilization, to fall in love, to raise children, to plan for the future in a cosmos where the ground itself might be temporary? There is no comfortable answer to that question, but the question itself is worth facing, because if the universe is truly metastable, then every moment of existence is borrowed time, and borrowed time, it turns out, is the only kind there is. Let us begin with the bubble itself. Not the abstraction of it, not the concept, but the physical reality of what would form if vacuum decay were to occur somewhere in the cosmos. Imagine a point in space. Any point. It could be in the void between galaxy clusters, where the density of matter approaches zero. It could be within a nebula surrounded by gas and dust. It could be, for all we know, somewhere in the space between your reading lamp and the wall behind it. The location does not matter. What matters is what happens at that location in the moment of nucleation. A quantum fluctuation occurs. This is not unusual. Quantum fluctuations happen constantly, everywhere, all the time. The vacuum of space is not empty in the classical sense. It seethes with virtual particles popping into existence and annihilating, with fields oscillating at their lowest energy states, with a kind of foam of probability that underlies all of reality. Most of these fluctuations are harmless. They create and destroy particles in pairs. They contribute to the Casimir effect, to the Lamb shift, to measurable phenomena that have been confirmed in laboratories around the world. They are part of the ordinary background hum of quantum field theory. But occasionally, rarely, in a metastable vacuum, a fluctuation can do something different. It can tunnel. Not through a physical barrier, but through an energy barrier. It can find its way from the false vacuum state to the true vacuum state, through the strange logic of quantum mechanics, where particles and fields do not have definite values but exist as probability distributions, and where transitions that would be classically forbidden become possible with some small, non-zero probability. When this tunneling occurs, a tiny region of space suddenly contains true vacuum instead of false vacuum. The Higgs field in that region, or whatever field is responsible for the vacuum energy, has dropped to its true ground state. The configuration of energy in that microscopic volume is now different from the configuration everywhere else. And here is where the physics becomes terrifying. The true vacuum has lower energy than the false vacuum. This is not a small difference. Depending on the specifics of the underlying physics, the energy density difference could be enormous. An energy density in general relativity is equivalent to mass. It curves space-time, it exerts pressure, and when you have a region of lower energy density surrounded by a region of higher energy density, something has to give. The boundary between the two regions, the wall of the bubble, is where this difference manifests. The wall is not made of matter in any conventional sense. It is a transition region where the Higgs field, or the relevant field, rapidly changes value. It is a kind of shock front, a discontinuity in the fabric of reality itself. And because the energy inside the bubble is lower than the energy outside, the wall is under tension. It wants to expand. It must expand. In normal physics, expansion costs energy. You have to push against something, you have to do work. But here, the expansion releases energy. The volume of true vacuum grows, and that growth converts the energy difference between the two vacuum states into kinetic energy of the wall itself. The more the bubble expands, the more energy is released, and the faster the wall moves. This is not a slow process. The wall accelerates. It does not merely move outward. It accelerates toward the speed of light, and asymptotically approaches it. Within an astonishingly short time, the wall is moving at velocities so close to the speed of light that the difference becomes meaningless from any practical standpoint. Let that sink in for a moment. A wall of altered reality, expanding at essentially the speed of light. Not slowing down, not losing energy, accelerating continuously, or maintaining its near-light velocity once achieved, converting the fabric of space itself into fuel for its own propagation. There is no air resistance in space. There is no friction. There is nothing to impede it. The wall will continue expanding until it runs out of false vacuum to convert, which in a universe of finite or even infinite extent could mean expanding forever. This is not a metaphor. This is what the equations predict. Now let us consider what happens at the wall itself. As the bubble expands, the transition region between false vacuum and true vacuum is incredibly thin. How thin depends on the specific parameters of the theory. But in many models, the wall thickness is on the order of the Planck length, or perhaps a few orders of magnitude larger. The Planck length is approximately 1.6 times 10 to the negative 35th meters. To put this in perspective, an atom is roughly 10 to the negative 10th meters across. The Planck length is to an atom as an atom is to a structure that would dwarf the observable universe. It is, for all practical purposes, the smallest length scale that has any physical meaning in our current understanding of physics. A wall that thin, moving at nearly the speed of light, would pass through any material object in a time interval so brief that no physical process could respond to it. Your neurons could not fire, chemical bonds could not rearrange. Light itself would not have time to traverse the width of a proton before the wall had already passed through your entire body, through the planet, through the solar system. And as the wall passes, everything changes, not physically destroyed in the conventional sense, not burned or crushed or torn apart, changed at a deeper level. The fundamental constants of nature on one side of the wall are different from those on the other side. The strength of the electromagnetic force might be different. The masses of elementary particles might be different. The very structure of the laws that govern chemistry, biology, gravity, all of it, would be different in the true vacuum than it was in the false vacuum. The analogy physicists sometimes use is a computer program being overwritten. Imagine every atom in your body as a small calculation running according to a set of rules. The rules are encoded in the vacuum state, in the configuration of the Higgs field, in the fundamental constants. When the wall passes, the rules change mid-calculation. The new rules have no reason to preserve the structure of the old calculation. The information that constituted you, that constituted the planet, that constituted the accumulated history of every civilization that ever existed, would be scrambled, converted, translated into configurations that the new physics permits, but that bear no resemblance to what came before. You would not experience the transition. You would not have time to experience anything. The wall would reach your nervous system and pass through it faster than a nerve signal could propagate across a single synapse. From your subjective perspective, there would be no moment of destruction. One instant, existence. The next instant, not existence, but not even a next instant in which to register the not existence. Just termination. This is not like any other cosmic threat we know of. Asteroid impacts are visible, they can be tracked. In principle, they can be deflected. Supernovae are bright. They can be predicted, at least in rough terms. Gamma-ray bursts give warning, if only for a few minutes. Black holes are gravitationally detectable long before you fall into them. Even the heat death of the universe, while inescapable, happens slowly enough that civilizations could adapt, migrate, husband resources, face the end consciously. But vacuum decay is invisible. The wall travels at the speed of light, which means it arrives at the same moment as any signal warning of its approach. You cannot see it coming because nothing can outrun it to tell you it is on its way. The light from the moment of nucleation, the photons that left the original bubble at the instant it formed, are travelling at exactly the same speed as the wall itself. They are, in a sense, part of the wall. By the time any evidence of the event could reach you, the event has already reached you. Let me put that in another way. Suppose vacuum decay began in the Andromeda Galaxy, 2.5 million light-years away. The wall would take 2.5 million years to reach us, but we would not know it was coming for 2.5 million years, because the light carrying the information about the event would also take 2.5 million years to arrive. We would learn about it and die from it in the same instant. Now suppose vacuum decay began somewhere much closer, 1,000 light-years away, 100 light-years away, 10 light-years away, 1 light-year away. The same logic applies. No warning, no detection. No time to contemplate or prepare or make peace with the end. Just existence, and then not. And here is the hardest part to sit with. It may already have happened. The observable universe is roughly 93 billion light-years in diameter. This is much larger than 13.8 billion light-years because the universe has been expanding while light has been travelling toward us. Light that left distant regions billions of years ago has been carried along by the expanding fabric of space-time, and the regions it left have continued to recede. The result is that we can see objects that are now much farther away than the light travel time would suggest. But we can only see things whose light has had time to reach us. Beyond the observable universe, there is more universe. We do not know how much more. It could be finite. It could be infinite. Current observations are consistent with both possibilities. The curvature of space appears to be flat or very nearly flat, which is consistent with an infinite universe. But it could also be consistent with a finite universe, large enough that we cannot detect the curvature with current instruments. If the universe is infinite, then the probability calculation changes dramatically. False vacuum decay has a probability per unit volume per unit time. Let us call it P. This probability is unimaginably small under normal conditions, something like 10 to the negative power of hundreds per cubic meter per year. In a finite universe, you can multiply this probability by the volume of the universe and the age of the universe and get a number that is still incredibly small. The expected number of nucleation events might be far less than 1. We might be essentially safe. But in an infinite universe, you multiply that probability by infinity. And any positive number multiplied by infinity is infinity. If the universe is truly infinite, then vacuum decay is not just possible somewhere. It is happening right now in infinitely many places. Infinitely many bubbles are nucleating. Infinitely many walls are expanding. Infinitely many regions are being converted from false vacuum to true vacuum at this very moment. The question then becomes not whether vacuum decay is occurring, but whether any of those bubbles are close enough to reach us. And this is where the cosmological horizon becomes relevant. The universe is not only expanding, it is expanding at an accelerating rate. This acceleration is driven by what we call dark energy, a form of energy inherent to the vacuum of space itself. Dark energy causes distant regions of the universe to recede from us faster and faster. Eventually, regions that are far enough away will be receding faster than the speed of light. This does not violate special relativity because it is not motion through space, but expansion of space itself. Those regions will be forever beyond our reach. Their light will never reach us. They will leave our cosmic horizon and disappear forever. This means that even if vacuum decay is occurring somewhere in the infinite universe, the resulting bubbles might never be able to reach us. If a bubble nucleates far enough away, in a region that is receding from us faster than the bubble wall is expanding toward us, the wall will never arrive. We will be protected not by physics but by geometry. The expansion of the universe creates a kind of cosmic shield, preventing sufficiently distant events from ever affecting us. But this protection has limits. The cosmic horizon is not absolute. It depends on when the event occurs. A bubble that nucleated early in the universe's history, when the expansion rate was different, might have had time to reach us. A bubble that nucleates nearby, within our cosmic horizon, would not be stopped by expansion. The shield only protects against sufficiently distant events, and it does not protect perfectly even against those. Moreover, we do not know the probability distribution of nucleation with enough precision to calculate the odds. The probability per unit volume depends on parameters we have not measured directly. The mass of the Higgs boson, the mass of the top quark, the detailed shape of the Higgs potential at energy scales far beyond what we can probe, the existence or absence of new physics that might stabilize the vacuum or destabilize it further. We have estimates, we have calculations, but they come with error bars, and those error bars matter when you are trying to determine whether civilization survives. Let me give you a sense of the numbers. The mass of the Higgs boson has been measured at approximately 125.25 billion electron volts, with an uncertainty of around 0.7 billion electron volts. The mass of the top quark has been measured at approximately 172.69 billion electron volts, with an uncertainty of around 0.3 billion electron volts. These are remarkably precise measurements, the product of decades of work by thousands of physicists at facilities like the Large Hadron Collider. But when you feed these numbers into the equations that determine the stability of the vacuum, you find something unsettling. The boundary between a stable vacuum and a metastable vacuum depends on the precise relationship between these masses. If the Higgs mass is high enough relative to the top quark mass, the vacuum is stable. If it is low enough, the vacuum is unstable, meaning it would decay immediately, which would be inconsistent with the obvious fact that we exist. And there is a range in between where the vacuum is metastable, where it is stable for now but unstable in the long term. The measured values place us in the metastable range, but just barely. We are close to the boundary with stability. If the top quark were slightly less massive, or the Higgs slightly more massive, we would be in the stable regime and there would be nothing to worry about. But we are on the other side of the line, in the region where vacuum decay is possible. And here is the troubling part. We are close enough to the boundary that the uncertainty in our measurements matters. When you take the error bars on the Higgs mass and the top quark mass into account, you find that the probability of the vacuum being stable is perhaps 5 to 10%. The probability of it being metastable is perhaps 90 to 95%. And there is a small but non-zero probability, maybe 1 or 2%, that the vacuum is actually unstable and that we have survived this long only by extraordinary luck. These are not abstract numbers. They represent our best current understanding of the fate of the universe. Physicists at CERN, the organisation that operates the Large Hadron Collider, have produced official reports on this question. They have calculated the probability of various outcomes. They have examined the implications, and they have concluded correctly that there is nothing to be done about it. If the vacuum is metastable, then it is metastable. We cannot change the fundamental constants. We cannot alter the shape of the Higgs potential. We can only measure and wait and hope. Stop and feel the weight of that. Scientists at one of the most sophisticated research facilities ever constructed by human beings have measured the properties of the universe and concluded that the ground beneath our feet might not be stable, and that there is nothing we can do about it except continue to live. This is not alarmism. It is not apocalypticism. It is the sober conclusion of peer-reviewed physics. There is one more aspect of the bubble that deserves attention before we move on. One more feature of vacuum decay that makes it different from every other catastrophe we can imagine. The bubble wall does not merely destroy, it creates. On the other side of the wall, where the true vacuum reigns, there is still a universe. There are still fields and particles and space-time and possibly energy and matter in some configuration. The true vacuum is not nothing. It is something. It is a different something than what we have now, but it is not void. We do not know what that something would look like. The physics of the true vacuum depends on which field configurations are stable at the true ground state. In some models, the true vacuum permits no atoms, no chemistry, no structure of any kind, just a smooth, featureless sea of energy with no way to form complexity. In other models, the true vacuum might permit different kinds of atoms, different kinds of chemistry, different kinds of physics that we cannot imagine, because we have never experienced anything like them. Some physicists have speculated, half seriously, that if vacuum decay occurred, entirely new forms of complexity might arise in the true vacuum. Different laws, different structures, different possibilities. Perhaps even different kinds of life, built on different principles, exploring a reality that we would not recognize. This is speculation. We have no way to calculate what the true vacuum would be like, because we do not know the details of the physics at the relevant energy scales. But the possibility is there. The universe would not end in the sense of becoming nothing. It would end in the sense of becoming something we have no part in. There is a terrible poetry in this. The bubble wall is not an eraser. It is a translator. It converts the universe from one language to another, and we do not speak the new language. Everything we are, everything we have made, everything we have loved and lost and built and destroyed would be translated into terms that do not preserve our meaning, and it would happen at the speed of light, and we would never see it coming. This is the reality of false vacuum decay, a bubble that forms without warning, expands without stopping, arrives without announcement, and transforms without mercy. It is not the death of the universe, but its metamorphosis, and we are the caterpillar that will not survive the cocoon. And yet we are still here. Trillions upon trillions of cubic light years have existed for 13.8 billion years, and no wall has reached us. Either we are extraordinarily fortunate, or the probability is even lower than we think, or there is something we do not understand that is protecting us. In the sections that follow, we will explore what that something might be. We will look at the physics beyond the standard model, the theories that might stabilize the vacuum, the mechanisms that might prevent nucleation. We will examine the arguments and the evidence and the hope, such as it is. But for now, sit with the bubble. Picture it expanding somewhere in the void, its wall of transformed reality sweeping outward through the darkness. Maybe it started 1 billion years ago in some distant galaxy. Maybe it started yesterday in the space between here and Alpha Centauri. Maybe it will never start at all. The universe keeps its counsel, and we, small and temporary and unprotected, go on. The question that haunts every physicist who has seriously considered vacuum decay is not whether it can happen. The mathematics is clear on that point. The question is why it has not happened already. Why, after 13.8 billion years of cosmic history, after countless quantum fluctuations in every cubic centimetre of space, after the violent birth of stars and the cataclysmic deaths of galaxies, has the bubble never come? Either we are witnessing an extraordinary streak of luck, the longest winning hand in the history of existence, or something is protecting us. Something in the physics we do not yet fully understand. To explore this question, we need to go beyond the standard model. We need to look at the theories that physicists have proposed to complete our understanding of reality. Theories that might stabilize the Higgs field, theories that might close the door on vacuum decay forever. And we need to be honest about what these theories predict, which is not always comforting. The first possibility is the simplest. Perhaps the standard model is incomplete not because something exotic is missing, but because something ordinary is missing. Perhaps there are additional Higgs particles that we have not discovered, particles that would change the shape of the Higgs potential in ways that eliminate the deeper minimum entirely. In the standard model, there is only one Higgs boson, particle discovered at the Large Hadron Collider in 2012, but extensions to the standard model often predict more. In some theories, there are 2 Higgs doublets instead of 1, leading to 5 different Higgs particles instead of just 1. In other theories, there are entire families of Higgs fields, each interacting with the others in complex ways, each contributing to the overall shape of the energy landscape. If additional Higgs particles exist at high energies, they would contribute to the running of the Higgs self-coupling, that crucial parameter that determines whether the Higgs potential turns over and plunges toward instability. The contributions could be positive, lifting the potential back up at high energies, eliminating the deeper minimum that makes our vacuum metastable. In this scenario, the universe would not be sitting on a false shelf at all. The shelf would be the true ground floor. There would be no lower level to fall to. This is an appealing possibility, but it comes with a problem. If additional Higgs particles exist at energies we can reach, we should have seen hints of them by now. The Large Hadron Collider has been searching for new Higgs states for over a decade, and so far nothing. The standard model Higgs remains stubbornly alone, exactly as predicted, offering no evidence that the particle spectrum extends beyond what we already know. Of course, the additional particles might exist at energies beyond the reach of the LHC. The collider can probe energies up to about 14 tera electron volts, which sounds impressive until you remember that the Planck scale, where gravity becomes strong and quantum effects become paramount, lies at 10 to the power of 19 gigaelectron volts. That is a factor of 1,000,000 billion beyond what the LHC can achieve. There is an enormous desert of energy between where our experiments end and where the truly fundamental physics lives, and anything could be hiding in that desert. So additional Higgs particles might exist, might stabilize the vacuum, and might remain forever beyond our ability to detect. This is philosophically uncomfortable. A safety mechanism we cannot verify is not much different from no safety mechanism at all, at least from the perspective of certainty. We would be taking it on faith that the physics at high energies is kind to us, and physics does not give us much reason to trust in kindness. The second possibility is more dramatic: supersymmetry. For decades, supersymmetry was the leading candidate for physics beyond the standard model. It is a beautiful mathematical framework that proposes a deep symmetry between the 2 fundamental types of particles, fermions and bosons. In the supersymmetric extension of the standard model, every known particle has a partner. Every fermion has a bosonic superpartner. Every boson has a fermionic superpartner. The electron has the selectron. The quark has the squark. The photon has the photino. The Higgs has the Higgsino. An entire shadow army of particles, each one related to the particles we know by this deep mathematical symmetry. If supersymmetry exists, it would transform the Higgs potential. The contributions from the superpartners would modify the running of the coupling constants in ways that almost universally stabilize the vacuum. The deeper minimum would be lifted or eliminated entirely, or rendered inaccessible. The metastability would vanish. The bubble would become impossible. For a generation of physicists, supersymmetry was not just a speculation. It was almost an expectation. The mathematics was so elegant, the consequences so beneficial, The problems it solves so fundamental that many researchers expected the Large Hadron Collider to find superpartners within months of turning on. The discovery was supposed to be straightforward. The particles were supposed to be there, waiting to be found, confirming the beautiful theory and stabilizing the universe in one triumphant moment. But the LHC found nothing. Year after year, collision after collision, the detectors searched for supersymmetric particles and came up empty. No selectrons, no squarks, no photinos, no gluinos. The experiments placed ever tighter constraints on where the superpartners could hide, pushing them to higher and higher energies, and still found nothing. The beautiful theory began to look like a beautiful fantasy. This does not mean supersymmetry is dead. The superpartners might exist at energies just beyond what the LHC can reach, waiting for a more powerful collider that may never be built. But the simplest versions of supersymmetry, the versions that were supposed to be most natural and most elegant, are now ruled out. If supersymmetry exists, it is hiding, it is complicated, it is not the safety net we hoped for. And here is the uncomfortable truth. If supersymmetry is not protecting us, and if additional Higgs particles are not protecting us, and if the standard model continues to hold all the way up to extremely high energies, then the metastability calculation stands. The vacuum remains false, the bubble remains possible, and we remain unprotected. There is a third possibility, one that physicists have explored in recent years with increasing interest. Perhaps the metastability is not a bug but a feature. Perhaps the universe is metastable by design, if design is even the right word. This idea connects to some of the deepest questions in physics. Why do the constants of nature have the values they have? Why is the mass of the Higgs what it is? Why is the universe apparently fine-tuned for complexity, for chemistry, for life? These questions have troubled physicists for decades, and one possible answer involves the multiverse. The multiverse hypothesis proposes that our observable universe is not all that exists. There may be other regions of space separated from us by vast distances, or by the very structure of space-time itself, where the constants of nature take different values, different Higgs masses, different coupling strengths, different numbers of dimensions, an infinite landscape of possibility, with our universe being just one island in an archipelago of alternative realities. If the multiverse exists, then the metastability of our vacuum might be explained by a kind of cosmic selection effect. Among all the possible universes, the ones that can contain observers, the ones that can develop complexity and life and creatures who ask questions about vacuum decay, might preferentially be the ones that sit on the edge of stability. Not too stable, because that might require fine-tuning of a different kind. Not too unstable, because those universes would have collapsed into the true vacuum long ago, before stars could form, or planets could cool, or life could arise. But metastable, balanced on the knife's edge, lasting long enough for the show to go on. This is the Anthropic argument. We find ourselves in a metastable universe not because metastability is rare, but because we could not exist in a universe that had already decayed. The bubble universes, the ones where the false vacuum collapsed in the first billion years, would be sterile. No observers, no questions, no awareness of their own demise. We exist, therefore we exist in a universe that has not yet destroyed us. The logic is almost tautological, but it has a strange power. The problem with the Anthropic argument is that it explains everything and predicts nothing. It tells us why we might find ourselves in a metastable universe, but it does not tell us anything about how long that metastability will last. It does not tell us whether the bubble will come tomorrow or in 10 to the power of 100 years. It does not provide safety, it provides only context. And there is a deeper problem, one that goes to the heart of what we mean by scientific explanation. The Anthropic argument suggests that we should not be surprised by metastability, but it does not tell us whether metastability is actually the case. It is an argument about our psychological response to the evidence, not about the evidence itself. The Higgs potential is what it is, regardless of whether observers exist to worry about it. If the deeper minimum is there, the bubble can form. Anthropic reasoning cannot prevent the quantum fluctuation that starts the cascade. It can only tell us why we have not yet been consumed. So let us return to the physics. Let us look more carefully at what would have to happen for a bubble to form, and whether there are mechanisms that might suppress that formation. The key concept is the bounce solution. In quantum mechanics, particles can tunnel through barriers that they classically could not overcome. This is the same phenomenon that allows radioactive nuclei to decay, that allows electrons to escape from atoms in strong electric fields, that allows the sun to shine by permitting protons to fuse despite their electrical repulsion. Tunneling is not speculative. It is one of the most thoroughly confirmed predictions of quantum mechanics. For the Higgs field, the barrier is not a physical wall in space, but a peak in the energy landscape. On one side is the false vacuum, our current comfortable state. On the other side is the true vacuum, the deeper minimum. In between is a ridge of high energy that the field would have to climb over classically. But quantum mechanics allows the field to tunnel through this ridge, to appear on the other side without ever having the energy to go over the top. The probability of tunneling depends on the shape of the barrier, its height and its width. The Coleman-de Lucia calculation that determines the bubble nucleation rate is essentially a tunneling calculation for a quantum field. The bounce solution is the path through the barrier, the route that the field takes as it tunnels from the false vacuum to the true vacuum. The nucleation rate depends on the action associated with this bounce, a mathematical quantity that measures how unlikely the path is. A larger action means a lower probability. A smaller action means a higher probability. In the standard model with the measured values of the Higgs and top quark masses, the action is enormous. The nucleation probability per unit spacetime volume is proportional to the exponential of negative the action, and the action is something like 10 to the power of 800 or higher in natural units. This is why the lifetime of the false vacuum is so long. The universe has not existed long enough, and does not contain enough spacetime volume for a single bubble to have formed with appreciable probability. But notice the fragility of this conclusion. It depends on the precise shape of the barrier, which depends on the precise values of the Higgs parameters, which depend on the precise values of the masses we measure. Small changes in the top quark mass could significantly change the action, and therefore the probability. If the true values of these masses are slightly different from our measurements, the lifetime could be shorter than we think. If there is new physics at high energies that modifies the potential, the lifetime could be longer or shorter or essentially infinite. This is why physicists at CERN and elsewhere care so much about measuring these parameters with increasing precision. Every decimal place of accuracy is a constraint on our fate. Every improvement in our knowledge of the top quark mass is a refinement of our understanding of how stable our existence might be. These are not academic exercises. They are, in a very real sense, survival calculations. There is another factor that affects the nucleation rate, one that we have not yet discussed: gravity. In flat space-time, without the curvature that gravity produces, the Coleman-de Lucia calculation gives a certain result. But we do not live in flat space-time. We live in a universe that is expanding, a universe with a positive cosmological constant, a universe where the geometry of space itself is changing over time. Gravity modifies the tunneling process in ways that can either suppress or enhance the nucleation rate. In some scenarios, gravity acts as a safety valve. The expansion of the universe, driven by dark energy, dilutes the vacuum energy in ways that could make the bubble nucleation harder. The bubbles that form might not grow as quickly, or might not form as often, because the expanding space-time is working against the tunneling process. This is not a reliable protection, but it is a factor that enters the calculation. In other scenarios, gravity makes things worse. If the false vacuum has a higher energy density than the true vacuum, which is almost certainly the case, then the interior of the bubble has negative vacuum energy relative to its exterior. This is the same as saying the interior has a lower cosmological constant. In the extreme case, the interior could have negative cosmological constant, which would mean the interior space-time is not expanding but contracting, collapsing inward on itself. The bubble would not just transform physics, it would create a crunching space-time within itself, a big crunch in miniature, ending not just matter but space and time themselves in that region. We do not know which scenario applies. The answer depends on the details of the Higgs potential, at energies we cannot probe, and on the unknown value of the vacuum energy in the true ground state. We are working with partial information, extrapolating from what we know to what we cannot measure, hoping that our extrapolations are correct. And this brings us to what might be the most important question of all. What could trigger a bubble? In the absence of any external influence, the nucleation is purely quantum. It happens, or it does not happen, according to probabilities that are, as far as we can tell, truly random. There is no cause in the classical sense, no event that triggers the fluctuation, no warning sign that precedes the collapse. The bubble simply appears, spontaneously, from the quantum foam of the vacuum itself. But external influences exist. The universe is not empty. It contains matter and energy, particles and radiation, gravitational waves and magnetic fields and cosmic rays. Could any of these trigger a bubble? Could there be events in the universe so violent, so energetic, that they push the Higgs field over the barrier instead of allowing it to tunnel? This question has been studied, and the answer is both reassuring and disturbing. In general, thermal fluctuations cannot trigger the decay. The temperature required to kick the Higgs field over the barrier would be extraordinary, many orders of magnitude hotter than the cores of the hottest stars, hotter even than the universe has been since the first fractions of a second after the Big Bang. No astrophysical event in the current universe could provide enough thermal energy to overcome the barrier. The Sun going supernova would not do it. 2 neutron stars colliding would not do it. A gamma-ray burst would not do it. These events are violent by human standards, but they are gentle by the standards of the Higgs potential. However, there are scenarios involving exotic objects that might be different. Black holes, for instance. As a black hole evaporates through Hawking radiation, it gets smaller and hotter. In its final moments, as it shrinks toward the Planck mass, the temperature becomes extraordinary, hotter than anything else in the universe, hot enough perhaps to probe the energy scales where the Higgs potential turns over. Some physicists have speculated that the final explosion of a black hole, the Planck scale burst of energy as it disappears completely, might be able to trigger a bubble nucleation event. Stephen Hawking himself considered this possibility in one of his later papers. He and his collaborators examined whether the presence of a black hole could seed vacuum decay, whether the intense curvature near the singularity could lower the barrier or catalyze the tunneling. The results were ambiguous. Some calculations suggested that black holes might increase the nucleation rate. Others suggested they might suppress it. The physics at these scales is simply not well enough understood to give a definitive answer. But think about what this means. There are black holes scattered throughout the universe. Stellar mass black holes in their billions, remnants of dead stars lurking in the darkness. Supermassive black holes at the centres of galaxies, containing millions or billions of solar masses. Intermediate black holes, primordial black holes perhaps formed in the early universe, black holes we have not yet detected and may never detect. If any of these evaporates completely, if any of these reaches the final moment of Hawking evaporation and explodes in a Planck temperature burst, it might be the trigger. It might be the random event that pushes one tiny region of space over the edge. The primordial black holes are particularly concerning. If they exist, some of them might have masses small enough that their evaporation timescale is comparable to the age of the universe. They might be evaporating right now somewhere in the cosmos, releasing energy at scales we cannot probe, and we would not know. We would not see them. They would be too small, too distant, too brief in their final burst. But if one of them triggered a bubble, we would find out eventually. At the speed of light, without warning. There is another potential trigger that has received attention in recent years. Cosmic strings. Cosmic strings are hypothetical defects in space-time, one-dimensional objects left over from phase transitions in the early universe. If they exist, they would be extraordinarily thin, thinner than an atom, but they would stretch across cosmic distances, threading through galaxies like invisible wires. They would be incredibly dense, containing immense amounts of mass energy in a tiny cross-section. And where they move through space, they would create disturbances in the quantum fields around them. Some theoretical work has suggested that cosmic strings could catalyze vacuum decay. The intense energy density along the string could lower the barrier for the Higgs field, making it easier for a bubble to nucleate in the vicinity of the defect. A cosmic string passing through our region of the universe might leave a trail of bubbles in its wake, each one expanding, each one threatening to consume everything it touches. We have not detected cosmic strings. Their existence remains hypothetical. But the fact that they could exist, that they could be present in our universe, and we would not necessarily know, adds another layer of uncertainty to our calculations. Another way the trigger could come, and then there is the possibility that some event in our own future might create the conditions for decay. Not an event that has already happened, but an event that we might cause. When the Large Hadron Collider was first proposed, some critics raised the concern that high-energy particle collisions might trigger catastrophic events, microscopic black holes, strange matter that converts ordinary matter into itself, and yes, vacuum decay. What if smashing particles together at 14 tera electron volts created a local condition energetic enough to nudge the Higgs field toward the true vacuum? The physicists who designed the LHC took these concerns seriously enough to study them in detail. The safety report they produced examined each scenario and concluded that the collisions at the LHC could not trigger vacuum decay for a simple and elegant reason. Cosmic rays have been doing the same thing for billions of years, and the universe is still here. Cosmic rays are particles from space that strike the atoms in the Earth's atmosphere, in other planets, in asteroids, in the surfaces of neutron stars, at energies far exceeding anything the LHC can produce. Nature has been running particle collision experiments for as long as there has been matter in the universe, at energies we cannot hope to achieve with any conceivable technology. If these collisions could trigger vacuum decay, it would have happened long ago. The fact that the universe still exists is powerful evidence that high-energy collisions do not pose this risk. This argument is reassuring. It is also logically sound. But it depends on the assumption that we understand all the relevant physics, that there is no subtlety we are missing, that the cosmic ray collisions are truly analogous to what happens at the LHC. And in science, especially in science that touches on questions of survival, assumptions deserve scrutiny. What if there is something special about collisions that happen inside the gravitational field of a planet rather than in the vacuum of space? What if there is something about the particular configuration of particles we create that differs from natural cosmic ray events? What if the decades of collisions we have accumulated create a cumulative effect that isolated cosmic ray impacts do not? These questions have been asked, and the answer is generally that they do not change the conclusion. The physics is robust. The cosmic ray argument is strong, but the questions themselves reveal a deeper truth. We're doing experiments at energies that probe the stability of the vacuum, and we are trusting that our understanding of that stability is correct. We are betting everything on our equations being right. So far, the bet has paid off. The LHC has operated for over a decade. It has collided protons at energies never before achieved in a laboratory. It has created exotic particles and measured their properties with exquisite precision, and nothing has gone wrong. No bubble has formed, no wall has spread. The universe continues. But the physicists who work on these questions know something that the public often misses. The LHC is not the highest energy accelerator we will ever build. Future colliders are being proposed, designed, discussed, colliders that would reach 100 tera electron volts or more. And beyond that, far beyond any technology we can currently imagine, lie energy scales where the Higgs potential definitely turns unstable. If we ever found a way to probe those scales directly, we would be approaching the dangerous region, the region where the barrier between the false vacuum and the true vacuum becomes thin and easily crossed. We will probably never build such a collider. The energy scales are too extreme, the technology too far beyond our reach. But the possibility exists in principle, and it raises a question that goes beyond physics into ethics, into philosophy, into the meaning of technological progress itself. Should there be limits on what we probe? If the vacuum is metastable, if there really is a lower ground state waiting to swallow us, do we have the right to push deeper and deeper into the energy scales where stability becomes uncertain? Do we have the right to take risks, however small, that could end not just human civilization but the entire observable universe? These are not idle questions. They are questions that future generations may have to answer if our understanding of physics improves and our technology advances. They are questions that connect the abstract mathematics of quantum field theory to the most concrete concerns of survival and responsibility. For now, we do not have answers. We have only the mathematics, the measurements, and the hope that the universe is kinder than our equations suggest. But perhaps the most unsettling aspect of vacuum decay is not what it would do to matter, or to physics, or to the structure of reality itself. It is what it would do to meaning, to purpose, to the entire project of existence as we understand it. Consider what we have built. Over 4 billion years, life on Earth has evolved from simple self-replicating molecules into a biosphere of staggering complexity. Trillions of organisms, millions of species, ecosystems that span from the deepest ocean trenches to the highest mountain peaks. and from that vast experiment in survival emerge consciousness. Beings that can look up at the stars and wonder. Beings that can write poetry, compose symphonies, prove mathematical theorems. Beings that can love each other, grieve for each other, sacrifice for each other. The entire arc of biological and cultural evolution, the long, slow climb from chemistry to meaning, has produced something genuinely remarkable. We are the universe becoming aware of itself. We are matter arranged in such a way that it can contemplate its own existence, and vacuum decay would erase all of it in an instant. Not just the achievements, not just the cathedrals and the libraries and the accumulated wisdom of 100 civilizations, but the potential, the future that never gets to happen, the questions that never get asked, the love that never gets felt, the consciousness that never awakens. Stop and feel the weight of that. When an asteroid strikes a planet, it destroys what exists at that moment, but the substrate remains. The laws of physics continue. Given enough time, new life could evolve, new consciousness could emerge. The loss is terrible, but it is not total. The universe retains the capacity to try again. When a star explodes and sterilizes its planetary system, the same principle holds. Somewhere else, around another star, the experiment continues. The pattern of life and mind finds new substrate, but vacuum decay is different. It does not destroy life on a planet. It does not sterilize a solar system. It does not even merely render the universe inhospitable to life as we know it. It rewrites the laws themselves. It transforms reality into something that cannot support any form of complexity whatsoever. No atoms, no chemistry, no possibility of structure or information or anything that could be called existence in any meaningful sense. It is not merely death, it is the elimination of the category in which death and life are both possible. The philosopher Nick Bostrom has written about existential risks, threats that could permanently curtail humanity's potential. He distinguishes between different types of catastrophe. Some disasters are recoverable. A nuclear war, even a devastating one, might leave survivors who could rebuild. A pandemic, even a severe one, might spare enough of the population to continue. These are terrible scenarios we should work hard to prevent, but they are not terminal in the deepest sense. The story continues, even if it continues in diminished form. Other disasters are terminal but local. The extinction of humanity would end our particular story, but the universe would continue. Other intelligences might evolve elsewhere, might even find traces of what we built, might wonder about the beings who once looked up at the same stars they now contemplate. Our ending would be tragic, but it would not be the ending of everything. Vacuum decay belongs to a third category entirely. It is not just an existential risk, it is an ontological risk. It threatens not just our existence, but the existence of existence itself. Not just the end of our story, but the end of all possible stories. Not just the death of consciousness, but the elimination of the substrate on which consciousness could ever arise. This is why some physicists who work on these questions report a particular kind of vertigo when they think carefully about the implications. It is one thing to contemplate one's own mortality. We all do that, to varying degrees. It is another thing entirely to contemplate the mortality of possibility itself, and yet there is something strange about this fear, something worth examining. The true vacuum bubble, if it exists, is expanding right now somewhere in the universe. Or it is not. Either the quantum fluctuation has occurred, or it has not. Either the bubble nucleated 1 billion years ago in some unimaginably distant galaxy, or no bubble exists anywhere in our cosmic horizon. We cannot know which is true. The information would travel at the speed of light, and the bubble wall travels at the same speed. There can never be a warning because the warning and the destruction arrive at exactly the same moment. So in a very real sense, the question of whether we should fear vacuum decay is already answered for us by the structure of space-time itself. If the bubble exists and is coming, we will never know it. We will simply end. If the bubble does not exist or is so far away that it will not reach us for billions of years, then our immediate fears are irrelevant. In neither case does the worrying accomplish anything. This is sometimes offered as a form of comfort. Why fear something you can never detect, never prevent, never even anticipate? The bubble either exists or it does not. Either it will arrive in the next microsecond or it will not arrive for 1 trillion years. And in either case, your fear changes nothing. So why not simply set the fear aside and continue living? This argument has a certain cold logic to it, but it misses something important about the nature of fear itself. Fear at its best is functional. It motivates us to avoid dangers, to prepare for threats, to take actions that increase our chances of survival. The fear of predators keeps prey animals alert. The fear of injury makes us careful. The fear of social rejection motivates us to maintain relationships. Fear serves a purpose because it guides behavior toward outcomes that matter. But the fear of vacuum decay cannot guide behavior. There is nothing to be done. No preparation, no defense, no warning system, no mitigation strategy. The fear is, in evolutionary terms, useless. It expends metabolic energy on a problem that has no solution, and yet we feel it anyway. Or at least, we feel something when we contemplate the possibility. A chill, a sense of vertigo, an instinctive pulling away from the thought itself. This reaction tells us something interesting about consciousness. We're not merely survival machines optimized for reproductive success. We are beings that can contemplate abstractions, including abstractions that have no practical relevance whatsoever. We can fear things that offer no opportunity for fear to be useful. We can worry about scenarios that lie entirely outside our control. This capacity is perhaps the most human thing about us. The ability to care about things we cannot change. The ability to feel awe at scales that dwarf us. The ability to experience existential dread about events that may or may not happen long after we are gone, long after everyone we know is gone, long after humanity itself may have vanished. Other animals do not lie awake at night contemplating the metastability of the Higgs potential. Other animals do not write papers about vacuum decay or record documentaries about the possible end of physics. Only humans do this. Only humans experience this particular flavour of cosmic terror. Is this a curse or a gift? Perhaps it is both. The curse is obvious. Awareness of these possibilities adds a background radiation of anxiety to existence. Even if we do not consciously dwell on vacuum decay, the knowledge that such things are possible changes our relationship to the universe. The night sky no longer seems quite as peaceful. The stability of matter no longer seems quite as guaranteed. The solidity of the ground beneath our feet no longer seems quite as solid. But the gift is subtler and perhaps more profound. The same capacity for abstract thought that allows us to fear vacuum decay also allows us to understand the universe in ways no other known creature can. We have decoded the laws of physics. We have traced the history of the cosmos from the Big Bang to the present day. We have predicted the existence of particles before we detected them, calculated the age of stars before we visited them, understood the structure of atoms before we could see them. This is remarkable. This is unprecedented in the history of life on Earth, and it is the same cognitive machinery that produces existential dread. You cannot have one without the other. You cannot have the capacity for cosmic understanding without also having the capacity for cosmic fear. They are two sides of the same coin, two aspects of the same strange gift that evolution gave us when it produced brains capable of symbolic thought and abstract reasoning. So what do we do with this knowledge? How do we live in a universe that might be built on unstable foundations? Some people respond with denial. They simply do not think about it. They focus on the immediate concerns of daily life, the problems they can actually solve, the relationships they can actually nurture. This is not necessarily a bad strategy. Life is finite regardless of vacuum decay. The sun will expand into a red giant in 5 billion years regardless of vacuum decay. There are plenty of other ways for everything to end that have nothing to do with the metastability of the Higgs field. Perhaps the wisest response is simply to accept that existence is temporary in countless ways and focus on making the most of whatever time we have. Others respond with what might be called cosmic acceptance. They lean into the terror rather than away from it. They contemplate the fragility of existence not to become paralyzed with fear, but to become more awake to the preciousness of what exists. If everything could end in an instant, then every instant that existence continues is a gift. Every sunrise is a minor miracle. Every conversation with someone you love is borrowed time. The awareness of fragility can heighten appreciation rather than diminish it. Still others respond with something approaching defiance. Yes, the universe might be unstable. Yes, the vacuum might decay. Yes, everything we have ever built and loved and hoped for might vanish in a light-speed cascade of physics rewriting itself. But until that happens, we persist. We continue. We ask questions and seek answers and build things and love each other and do all the things that conscious beings do. We refuse to let the possibility of ending stop us from continuing. There is something almost heroic about this stance. The knowledge of mortality, whether personal or cosmic, does not have to be paralyzing. It can be motivating. It can be a reminder that time is finite and therefore valuable. It can be a spur to action rather than an excuse for resignation. The philosopher Albert Camus wrote about a different kind of absurdity, the absurdity of seeking meaning in a universe that offers none. But his conclusion applies here as well. We must imagine Sisyphus happy, he wrote, because the struggle itself is enough to fill a heart. The same might be said of conscious beings in a metastable universe. We must imagine ourselves happy, or at least engaged, because the alternative is to surrender to a fear that accomplishes nothing. And perhaps there is one more response worth considering, a response that lies somewhere between acceptance and defiance. It is the response of wonder. Think about what vacuum decay actually represents. It is the possibility that the universe is even stranger and more complex than we imagined, that the vacuum itself has structure, that empty space is not really empty, that the laws of physics are not fixed eternal truths, but contingent features of a particular cosmic state, that there might be other ways for reality to be organized, other configurations of fields and forces, other possible universes hiding inside the one we know. This is terrifying, yes, but it is also wondrous. The same equations that describe the danger also describe a reality far richer than common sense would suggest. The quantum field theory that predicts metastability also predicts the extraordinary success of the Standard Model, the precise calculations that match experiment to 12 decimal places, the deep mathematical beauty that underlies the structure of matter. The universe that might destroy us is also the universe that created us, that sustains us, that produced through blind physical processes the very consciousness that now contemplates its own fragility. There is something almost sacred about this. Not sacred in a religious sense, perhaps, but sacred in the sense of deserving awe and reverence. We are temporary patterns in a vast cosmic process. We are made of atoms forged in ancient stars. We are the universe looking back at itself with curiosity and fear and wonder. And whether that universe is stable or metastable, whether it will last forever or end in a light-speed bubble of transformed physics, the fact that it exists at all is extraordinary. The fact that we exist at all is extraordinary. The fact that anything exists rather than nothing is perhaps the deepest mystery of all. Vacuum decay threatens to end all of this. But it also, in a strange way, illuminates why all of this matters. The more fragile existence is, the more precious it becomes. The more we understand the ways it could end, the more we appreciate that it continues. The awareness of death, whether personal or cosmic, is the shadow that gives meaning to life. This is not a comfortable conclusion. It does not make the fear go away. But it offers something that fear alone cannot provide. It offers a framework for living with knowledge that is too vast and too strange for our evolutionary psychology to easily process. We are beings that evolved to avoid predators on the African savanna. Our brains are optimized for immediate threats, for problems that can be solved through action, for fears that can be assuaged through effort. Vacuum decay fits into none of these categories. It is a threat we cannot see, cannot prevent, cannot even anticipate. It operates on scales that make our individual lives seem vanishingly small, and yet we persist, we continue, we ask questions and seek answers. There is a particular kind of courage in this. Not the courage of facing a threat you can fight, but the courage of facing a truth you cannot change. The courage of looking at the mathematics honestly, following the equations where they lead, acknowledging the possibilities without looking away. This is what physicists do every day. They study vacuum stability not because they expect to find a way to prevent decay, but because they want to understand. They measure the Higgs mass and the top quark mass not to save the universe, but to know it. They run the equations and publish the papers and attend the conferences because the alternative is ignorance, and ignorance is not really an option once you have glimpsed what knowledge is possible. The same might be said of anyone who contemplates these questions. We learn about vacuum decay not because the learning protects us, but because the learning is itself valuable. Understanding is its own reward. Knowledge, even terrifying knowledge, is better than comfortable illusion. This is the fundamental bet that science makes, that truth matters, that understanding is worth pursuing regardless of where it leads. that the universe deserves to be known, even the parts of it that frighten us. Vacuum decay frightens us. Let there be no pretending otherwise. It is one of the most disturbing possibilities in all of physics, a scenario in which everything we have ever valued could be erased without warning and without recourse. It challenges our assumptions about stability, about meaning, about the very permanence of the laws that make existence possible. But it is also, in its way, beautiful. The equations are elegant. The physics is deep. The connections to fundamental questions about the nature of space and time and matter are profound. If we had to choose between a universe that was simple and stable, but ultimately boring, and a universe that was complex and contingent and frightening and fascinating, we might, upon reflection, choose the latter. The danger and the wonder come together. And so we arrive at a strange place, a place where terror and awe coexist, where the same knowledge that disturbs us also illuminates us, where the fragility of existence points toward its preciousness. The bubble may be out there, expanding at the speed of light, erasing everything in its path, or it may not exist at all. Either way, we are here now. We are conscious now. We are asking these questions now. That has to mean something, even if we cannot say exactly what. Perhaps the strangest aspect of vacuum decay is not what it would do, but what it reveals about the nature of doing itself, about causation, about the very structure of events unfolding in time. We speak of the bubble as though it acts, as though it expands, as though it destroys. But this language conceals something fundamental about the physics. The bubble does not choose to expand, it does not intend to destroy, it does not even, in the deepest senses, do anything at all, it simply is. The true vacuum state has lower energy than the false vacuum state. The boundary between them propagates outward at the speed of light, because that is what boundaries between different vacuum states do when one has lower energy than the other. There is no agency, no malice, no purpose, just geometry and energy and the inexorable logic of field theory. This is perhaps the hardest thing for human minds to accept. We are built to interpret the world in terms of agents and intentions. When something happens, we look for someone or something that made it happen. When something threatens us, we look for a threat that can be reasoned with or fought or fled from. The bubble offers none of these handles. It is not an entity. It is not an event in the ordinary sense. It is a state transition, a phase change, a rearrangement of the underlying structure of reality. Think of it this way. Imagine you are a character drawn on a sheet of paper. Your entire existence consists of the two-dimensional surface of that paper, the marks that define you, the relationships between you and other figures, the very geometry of your world. All of it exists on and depends upon the paper itself. Now imagine that the paper begins to burn. The fire advances across the surface, consuming everything in its path. From your perspective inside the two-dimensional world, this would seem like the approach of some terrible destructive force. You might attribute will to it. You might see it as an invader, an enemy, a presence advancing toward you with destructive intent. But from outside the paper, the truth is different. The fire is not an agent. It is a process, a chemical reaction in which the cellulose of the paper combines with oxygen and releases energy. The paper is being transformed into ash and gas and heat, and this transformation proceeds according to the laws of chemistry, with no regard for the figures drawn on the surface. The fire does not intend to erase you. It does not even know you exist. It is simply what happens when paper burns. Vacuum decay is like this, but stranger. The bubble is not burning the universe. The bubble is the universe transitioning from one state to another, and the figures drawn on the paper, the galaxies and stars and planets and people, are not being attacked by the transition. They are part of the transition. They are configurations of the false vacuum that are being reconfigured as configurations of the true vacuum. Or more precisely, they are configurations that cannot exist in the true vacuum, and so they simply cease to be. This is why the question of whether vacuum decay is fast or slow, painful or painless, is ultimately beside the point. The question assumes that there is a you that experiences the transition, a consciousness that either suffers through the change or is mercifully anesthetized by its speed. But the physics suggests something more radical. There is no transition for you. There is only the transition of the structure that currently instantiates you, from a configuration that permits consciousness to one that does not. The experiencer does not survive into the new state to have an experience of that state. The experience simply terminates. This is not like death as we normally conceive it. Normal death involves the cessation of a particular biological process within a universe that continues. The atoms that composed you disperse and are incorporated into other structures. The world goes on, even though you do not. There is continuity around your discontinuity. With vacuum decay, there is no around. The discontinuity is total. The very framework within which continuity could be measured is itself erased. Some philosophers have argued that this should actually be less frightening than ordinary death. In ordinary death, there is a sense in which the world continues without you, indifferent to your absence. The party goes on, but you have been asked to leave. With vacuum decay, there is no party. There is no indifference. There is nothing at all that fails to include you, because there is nothing at all. This is supposed to be consoling. There can be no loss in a state where there is nothing to lose, no absence where there is nothing relative to which absence could be measured. But I'm not sure this reasoning actually works. The terror of vacuum decay is not about the state of non-existence itself. The terror is about the transition, about the fact that everything you value, everything you love, everything you have worked for and hoped for and believed in, could be erased without warning. The transition is what matters, not the afterward. And the transition, even if instantaneous, even if experientially null, still represents the loss of something real. The universe contains structure and complexity and consciousness right now. The universe, after a complete vacuum decay, would not. The difference is not nothing. The difference is everything. There is a concept in information theory called the black hole information paradox, which asks what happens to the information that falls into a black hole. Does it disappear when the black hole eventually evaporates? Is it somehow encoded in the Hawking radiation? The question matters because the laws of quantum mechanics, at their deepest level, seem to preserve information. A process that truly erased information would violate something fundamental about how the universe works. Vacuum decay presents a similar puzzle, but worse. When the bubble engulfs a region of space, what happens to the information that was encoded in the physical structures within that region? The atoms, the molecules, the patterns of energy and matter that constituted galaxies and planets and minds. Where does all of that go? The short answer is that it does not go anywhere. It is simply replaced. The field configuration changes, and the new configuration does not contain the old information any more than a smooth pond contains the information about the stone that once rested on its bottom, before the mud swallowed it whole. This might seem like a violation of information conservation, and in a sense, it is, or rather, it might be. The truth is that physicists do not fully understand how information behaves at the boundary between different vacuum states. The question requires a more complete theory of quantum gravity than we currently possess. String theory offers some frameworks for thinking about this. Loop quantum gravity offers others, but there is no consensus, no clear answer, no certainty about whether the information in our universe would truly be lost or somehow preserved in the transition. Some theorists have proposed that the information might be encoded in the boundary itself, in the structure of the bubble wall, in some holographic sense that we do not yet understand. Others argue that the question is meaningless, because information is defined relative to a set of physical laws, and when those laws change, the concept of information itself changes with them. Still, others suggest that the information is simply destroyed, and that vacuum decay is therefore one of the few genuinely irreversible processes in the universe. We do not know. The honest answer is that we do not know. And that uncertainty adds another layer to the existential strangeness of the whole scenario. Not only might everything be destroyed, but everything might be truly destroyed, in a sense that goes deeper than any destruction we have ever contemplated. Let me try to give you a feel for how this changes the picture. In ordinary cosmology, we imagine that the history of the universe is something like a story. Events happen in sequence. Causes lead to effects. The past determines the present, which constrains the future. Even if the story eventually ends, in heat death, in a big crunch, in some other cosmological finale, the story itself remains coherent. It was told. It happened. The fact that it ended does not erase the fact that it occurred. Vacuum decay threatens to undermine even this. If the information is truly destroyed, then in what sense did the story happen? If there is nothing left that remembers, nothing that preserves the pattern, nothing that bears the trace of what once was, then the ontological status of the past becomes uncertain. Did we exist if nothing remains that could, even in principle, contain evidence of our existence? This is a question for philosophers as much as physicists, but it is a question that physics has forced upon philosophy. There are those who argue that existence is in the present, that the past has already ceased to exist, and the future does not exist yet, and the only thing that truly exists is the momentary slice of now. On this view, vacuum decay would simply accelerate what is already happening, the constant annihilation of the present moment by the next present moment. The past is already gone, the bubble just makes that truth more vivid. But there are other views. Some physicists, following the implications of relativity, argue that all moments of time are equally real, that the distinction between past and present and future is a feature of consciousness rather than a feature of the universe. On this view, called eternalism or the block universe, your past self still exists, is still there in the block, is still just as real as your present self. The flow of time is an illusion, a feature of how conscious beings experience the block, not a feature of the block itself. If this view is correct, then vacuum decay might look different. The bubble would not be erasing the past. The past would still be there, in the block, just as real as it ever was. The bubble would simply be a boundary within the block, a surface separating two different kinds of physics. Everything on one side of the boundary would be as real as everything on the other side. The transition would not be annihilation but transformation. I offer this not as a consolation but as an illustration of how deep these questions go. The interpretation of vacuum decay depends on the interpretation of time itself, on questions that physics alone cannot answer, on choices that we make about the metaphysical framework within which we understand the mathematics. The equations do not tell you whether the past is real. The equations describe relationships between quantities. The meaning of those relationships, the ontological status of the entities they describe, the ultimate nature of the reality they model. These are questions that require more than calculation. They require interpretation. And interpretation is precisely what scientists have been doing, in different ways, since the possibility of vacuum decay was first understood. Some interpret the metastability as evidence that our universe is fine-tuned, a special case among many possible cosmologies, perhaps the product of selection effects within a multiverse. Others interpret it as evidence that our current theories are incomplete, that a more fundamental framework will resolve the instability and reveal our vacuum to be more stable than it appears. Still others accept the metastability at face value and incorporate it into their worldview, acknowledging that we live in a contingent universe, one that might have been otherwise and might yet become otherwise. Each interpretation carries implications. The multiverse interpretation suggests that there are infinitely many bubbles, infinitely many regions of space with different vacuum states, infinitely many versions of the cosmic story playing out in parallel. Some of these regions support life. Most do not. We exist in one that does, not because it is special, but because we could not exist anywhere else. This is the anthropic principle, applied to the deepest level of physical law. The incompleteness interpretation suggests that the current data are misleading, that better measurements or better theories will change the picture. Perhaps the Higgs mass is not exactly what we think it is. Perhaps the top quark mass will shift with more precise experiments. Perhaps there are new particles we have not yet discovered, particles that would alter the running of the coupling constants and stabilize the vacuum. This interpretation keeps hope alive that the danger is not real, that the metastability is an artifact of ignorance rather than a feature of nature. The acceptance interpretation suggests that we simply live with uncertainty, that we acknowledge the possibility without letting it paralyze us, that we continue our lives and our science with the awareness that absolute stability was never guaranteed. This is perhaps the hardest interpretation psychologically, but it might also be the most honest. It refuses the false comfort of certainty in either direction. It sits with the not knowing. I suspect that different people will find different interpretations compelling, and that the choice will depend as much on temperament as on evidence. Some minds are drawn to explanations that make the universe safe and comprehensible. Others are drawn to explanations that preserve the strangeness, that resist premature closure, that leave room for mystery. Vacuum decay is strange enough to accommodate many interpretations, and humble enough about our current knowledge to resist settling the question definitively. What we can say is that the question is real. The mathematics is real. The measurements are real. The possibility is real. Whatever interpretation we adopt, we cannot escape the underlying fact that the stability of our vacuum is not guaranteed by any known principle, that the measurements we have made are consistent with metastability, that the physics we understand suggests a universe balanced on a knife's edge. And there is something else we can say, something that connects all of this to the human project of understanding, to the act of science itself, to the reason we study these questions at all. The fact that we can understand this is remarkable. The fact that beings who evolved to find mates and avoid predators and secure food can comprehend the quantum field theoretic vacuum structure of the universe. This is not a small thing. It suggests something about the relationship between mind and cosmos, something about the depth of reality that is accessible to reason, something about the strange fit between human cognition and the mathematical structure of nature. We are not outside the universe looking in. We are inside the universe made of the same fields whose stability we are analysing. The electrons in your brain are excitations of the same electron field that would be transformed by a vacuum decay event. The Higgs field that gives you mass is the same Higgs field that might tunnel to a lower energy state. You are not separate from the physics you are contemplating. You are an expression of it. This creates a peculiar kind of intimacy with the subject. When we study vacuum decay, we are studying ourselves. We are studying the conditions of our own existence, the contingencies that permit us to be here at all, the factors that determine whether here will continue to exist. This is not abstract physics. This is the physics of everything. There is a tradition in philosophy called phenomenology that studies experience from the inside, that takes consciousness as its starting point rather than its explanandum. Phenomenologists ask what it is like to perceive, to think, to feel, to be. They bracket the question of what exists independently of experience and focus on the structure of experience itself. Vacuum decay might seem like the opposite of a phenomenological question. It concerns the objective structure of reality, the behaviour of quantum fields, the stability of the cosmos. It has nothing to do with how things seem and everything to do with how things are. But I think the opposition is not so clean, because the question of vacuum decay is ultimately a question about the conditions of possibility for there to be any seeming at all. It is a question about whether consciousness, experience, the felt quality of being alive, whether all of this rests on a stable foundation or a precarious one. And that question, however abstract its mathematical formulation, connects directly to the lived experience of being a conscious being in an uncertain universe. When you lie awake at night and wonder about the meaning of existence, you're not doing quantum field theory, but you are doing something related. You're asking about the structure of the reality you find yourself in, about the grounds of your being, about the nature of the stage on which your life is performed. Vacuum decay suggests that the stage itself is provisional, that the theatre might close, that the performance depends on conditions that are not guaranteed. This might seem like a reason for despair, but it might also be seen differently. The fact that the stage is provisional makes the performance more precious. The fact that the conditions are not guaranteed makes it more remarkable that they are met. We exist in a universe that permits our existence, in a vacuum state that allows the physics we depend on, in a configuration of fields that happens to support the complexity of life and mind. This is not nothing. This is, in some sense, everything. The philosophers speak of gratitude as a response to the givenness of existence. Not gratitude to anyone or anything necessarily, but gratitude that there is anything at all, that the universe exists, that it permits consciousness, that we are here to witness it, however briefly, however contingently. Vacuum decay deepens this gratitude by revealing just how contingent our existence is. We are not here because the universe had to produce us. We are here because of a particular configuration of fields and masses and coupling constants that happens to be stable enough for now to permit our emergence, for now. Those two words carry a weight that is difficult to convey. They contain the entire existential situation in miniature. We exist for now. The vacuum is stable for now. The physics permits life for now. Nothing guarantees the continuation of any of this. Nothing ensures that now will extend indefinitely into the future. And yet here we are, asking questions, seeking understanding, reaching toward truths that transcend our immediate circumstances. The very act of contemplating vacuum decay is a kind of defiance, or perhaps a kind of affirmation. We persist in wanting to know, even when what we might learn is terrifying. We refuse the comfortable ignorance that would protect us from disquieting truths. We choose knowledge over illusion, understanding over denial, engagement over withdrawal. This is what it means to be human, I think. To be finite beings who reach for the infinite. To be mortal beings who contemplate eternity. To be fragile beings who study the forces that might destroy us. We do this not because it is comfortable, but because it is necessary. Because the alternative is to live in a smaller world, a world bounded by our fears, a world that pretends to certainties it does not possess. The physicists who study vacuum stability are not different from the rest of us in this regard. They just have access to more precise formulations, more sophisticated tools, more developed frameworks for asking the questions. But the questions themselves are universal. Everyone, at some level, wonders about the nature of reality. Everyone asks whether existence is secure or precarious. Everyone wants to know what lies beneath the surface of appearances. Vacuum decay is one answer to that question, a partial answer, an uncertain answer, an answer that raises more questions than it resolves, but an answer nonetheless. An answer that says the surface is thin, the stability is provisional, the ground beneath your feet is solid only because of a particular configuration of quantum fields, and that configuration could change. This is not the whole story. There is more physics to discover, more mathematics to develop, more measurements to make. The future might reveal that the vacuum is more stable than current data suggest, or it might confirm the metastability, or it might uncover entirely new possibilities that we have not yet imagined. Science is a process, not a conclusion. The story is still being written. But whatever the future reveals, certain things will remain true. We exist, we are conscious, we ask questions, and we live in a universe that, however vast and strange and potentially dangerous, permits all of this to happen. The permission is not guaranteed, but it is granted for now, and that granting is worth contemplating. The bubble may be out there. It may be expanding at this very moment, crossing the unimaginable distances between galaxies, silent and invisible and unstoppable. Or it may not exist at all, may never nucleate, may remain a theoretical possibility forever unrealized. We cannot know. We cannot prepare. We cannot do anything except continue. And continuing in the face of that uncertainty is its own kind of answer. Not an answer to the physics, but an answer to the existential question that the physics raises. How should we live, knowing what we know? How should we be in a universe that might not let us be indefinitely? The answer is not given by the equations. The answer is given by how we respond to the equations, by whether we flinch from the knowledge or embrace it, by whether we let the fear paralyze us or let the wonder inspire us, by whether we see the contingency as a reason for despair or a reason for gratitude. The universe does not tell us how to feel about it. The universe does not care how we feel about it. The universe simply is what it is, a vast arrangement of fields and forces and structures, some of which happen to support our existence, some of which might someday erase it. Our response to this is up to us. Our interpretation is up to us. Our meaning is up to us. And that, perhaps, is the deepest lesson of vacuum decay. Not a lesson about physics, though there is plenty of physics to learn. Not a lesson about danger, though the danger is real. But a lesson about meaning, about the fact that meaning is not found in the universe, but made by those who inhabit it, about the fact that we are not passive recipients of cosmic truth, but active creators of human significance, about the fact that even in the face of potential annihilation, the choice of how to live remains our own. The bubble cannot take that from us. Whatever else it might destroy, it cannot destroy the meaning we have made before it arrives. That meaning was real when we created it. It is real now as we contemplate it, and it will remain real in whatever way reality permits, for as long as reality permits anything at all. This is cold comfort, perhaps, but it is not nothing. It is the recognition that human life has value, not because it is eternal, but because it is lived. That consciousness has significance not because it is permanent, but because it is present. That the questions we ask matter not because they will be answered forever, but because they are asked at all. The metastable vacuum trembles beneath us, a foundation that might hold for trillions of years, or might collapse tomorrow. We cannot know which. We can only know that we are here, now, asking the questions, seeking the answers, living the lives that the universe has somehow permitted us to live. And for now that is enough. It has to be enough. Because it is all we have. The fire burns low, the night grows deep, and we have travelled a very long distance together, through equations and experiments, through history and hypothesis, through the strange landscape where physics meets philosophy, and both dissolve into wonder. We have stared into the possibility that our universe is not what it appears to be, that the ground beneath all existence might be elevated, temporary, waiting, that somewhere in the vast darkness between galaxies, a bubble of true vacuum might already be racing toward us at the speed of light, carrying with it the end of everything we know and the beginning of something we cannot imagine. And now, at last, we must ask the question that has been waiting patiently beneath all the others, the question that makes the physics personal, the question that transforms abstract cosmology into something felt in the chest, something that matters in the hours before sleep. What do we do with this? Not what should the physicists do, though they have their experiments and their theories and their careful measurements. Not what should the governments do, though there is nothing any government could do even if it wanted to. But what do we, as conscious beings living out our brief span on this particular planet in this particular galaxy, do with the knowledge that everything might end without warning, without cause, without meaning? The honest answer is that we do nothing. Not because the knowledge is unimportant, but because there is nothing to do. This is perhaps the most unusual feature of vacuum decay as an existential threat. Every other danger that humanity faces comes with at least the possibility of response. Asteroid impacts can be predicted and potentially deflected. Climate change can be measured and potentially mitigated. Pandemics can be studied and potentially contained. Nuclear war can be avoided through careful diplomacy and mutual deterrence. Even the eventual death of our sun, billions of years in the future, is in principle addressable by a sufficiently advanced civilization that could migrate to other star systems. But vacuum decay offers no such purchase. There is no early warning system that could detect an approaching bubble. There is no technology that could slow it down or divert it. There is no shield that could protect even a single atom from the rewriting of physics itself. There is no bunker deep enough, no spacecraft fast enough, no plan comprehensive enough. The bubble arrives at the speed of light, which means it arrives precisely when we first see it, which means we never see it at all. There is no gap between detection and destruction, no moment to say goodbye, no time for fear or regret or anything at all. This is not something we can fight. This is not something we can flee. This is not even something we can face. In any meaningful sense of that word, we can only live, knowing that living might end at any instant, and that the ending would be so absolute that we would never know it had happened. And yet the sun still rises, and yet the coffee still tastes the way coffee tastes, and yet the faces of the people we love still look the way they look, still carry all the weight of memory and connection and hope that they have always carried. And yet the questions still burn in our minds, the curiosity still drives us forward, the wonder still catches in our throats when we look up at the night sky and contemplate the sheer improbability of our existence. The bubble changes none of this. The possibility of sudden annihilation does not make the coffee taste different. It does not make the faces less beautiful. It does not make the questions less compelling. If anything, it makes all of these things more vivid, more precious, more worthy of attention. Not because they might end, though they might, but because they exist at all, in a universe that did not have to permit them, that had no obligation to create minds capable of appreciating the improbability of their own existence. This is the strange gift that vacuum decay gives us, if we are willing to receive it. Not the gift of safety, which it explicitly denies, not the gift of permanence, which it renders impossible, but the gift of clarity, the gift of seeing our situation as it actually is, stripped of the comfortable illusions that make life feel more secure than it has ever been. We were never safe. Long before anyone understood quantum field theory, long before Hawking contemplated the cosmological implications of scalar fields, long before the Higgs boson revealed its peculiar mass, we were never safe. The universe has always been vast and indifferent and filled with processes that could end human existence without noticing that human existence was ever there. The dinosaurs did not know about the asteroid until it arrived. The species that came before them did not know about the volcanic eruptions or the ice ages, or the slow drift of continents that would reshape the world and make their environments uninhabitable. Existence has always been contingent. We have always lived on borrowed time. What vacuum decay does is make this contingency visible in a particularly stark way. It removes the middle distance of danger, the comfortable zone where we can imagine preparing and responding and surviving. It collapses the spectrum of existential risk down to a single point. Either the bubble is coming or it is not, and either way, there is nothing to do about it. This is terrifying if you need the illusion of control, but it is clarifying if you're willing to let go of that illusion and see what remains. What remains is everything that matters, everything that has ever mattered, everything that will ever matter, for as long as matter exists to matter to anyone. The relationships we build, the art we create, the questions we ask, the answers we find, the moments of joy and the moments of sorrow, and the vast stretches of ordinary time in between when we are simply alive, simply conscious, simply present in a universe that somehow permits presence. The bubble cannot give these things meaning, but the bubble cannot take their meaning away either. They mean what they mean because of how they are lived, not because of how long they are remembered. They are valuable in themselves, in the living of them, regardless of whether that living continues for another second or another trillion years. This is not optimism. This is not a silver lining. This is not a way of making the danger feel smaller than it is. The danger is real. The possibility is genuine. The physics is solid. If the Higgs field does sit in a false vacuum, then the universe as we know it exists in a state of profound impermanence, and there is nothing we can do to change that. But the meaning of our lives does not depend on changing it. The meaning of our lives depends on living them, fully and attentively and with as much wisdom as we can muster in whatever time we have. Consider the alternative. Consider what it would mean to live in genuine terror of vacuum decay, to let the possibility poison every moment, to see in every sunrise the shadow of the approaching bubble, to hold every person you love at a distance because they might be erased at any instant. This is a coherent response to the knowledge. It is logically consistent with the facts, but it is not a good response. It does not make the bubble less likely. It does not make the danger smaller. It only makes the life you are living less worth living, less filled with the joy and connection and wonder that are possible, less worthy of the consciousness that is aware of itself and its situation. The bubble, if it exists, will arrive whether you are terrified or at peace. The end, if it comes, will come whether you have spent your days in joy or in dread. You do not get a better outcome by worrying more. You do not gain additional seconds by holding your breath. The only variable within your control is the quality of the time you have, and that quality is not improved by fear. This is not a philosophical trick. This is not a psychological coping mechanism. This is the logical consequence of the physics itself. If there is truly nothing to be done, then doing nothing becomes the rational response. And doing nothing, in this context, means living. It means continuing. It means investing in the things that make life valuable, even though their value is not guaranteed to persist. It means accepting that uncertainty is not a temporary condition to be overcome, but the permanent state of all existence, and finding within that uncertainty a space for meaning. The ancient philosophers knew this, though they did not know about quantum field theory. The Stoics taught that we should concern ourselves only with what is within our control, and accept with equanimity everything that is not. The Buddhists taught that attachment to permanence is the root of suffering, and that wisdom lies in recognizing the impermanence of all things. The Epicureans taught that death is not to be feared because where death is, we are not, and where we are, death is not. These are not identical doctrines, but they share a common thread. The recognition that anxiety about what cannot be changed is not only useless but harmful, that the only moment we ever have is this one, and that how we inhabit this moment is the entire substance of how we live. Vacuum decay is the ultimate test case for this wisdom. It is the danger that cannot be prepared for, the end that cannot be seen coming, the annihilation that cannot be mourned because there would be no one left to mourn. It strips away every illusion of control and leaves only the bare fact of consciousness, present and aware, existing in a universe that might not permit existence for much longer. And in that stripped-down state, the question becomes very simple. Not, how do we survive? Because survival is not guaranteed. But, How do we live? Because living right now is all we can do. The answer is not given by physics. Physics tells us what the universe is. It does not tell us what the universe means. It does not tell us how to respond to what we learn. Those questions are ours to answer with whatever resources we have: our values, our traditions, our communities, our capacity for love and wonder and courage in the face of uncertainty. And here, at last, we come to the heart of it. The reason this topic matters, beyond the scientific fascination, beyond the intellectual puzzle, beyond the sheer strangeness of contemplating the possibility that reality itself might be rewritten. It matters because it forces us to confront what we already knew, but preferred not to think about: that existence is not owed to us, that consciousness is not guaranteed, that the universe did not have to make room for creatures who could ask questions about its nature. We are here by accident, or by chance, or by some process so complex that we may never fully understand it. We're here because conditions aligned, because forces balanced, because the vacuum happened to be metastable, long enough for stars to form and planets to coalesce, and life to emerge, and minds to develop, and questions to be asked. We are here because we are here. And that circularity is not a flaw in the reasoning, but the entire point. There is no deeper justification. There is no external validation. There is only the fact of our existence, improbable and contingent and unspeakably precious. The bubble, if it comes, will end all of this. The carbon in our bodies will be reconfigured according to new physics. The electrical patterns that constitute our thoughts will be disrupted and dissolved. The meaning we have made will have no one left to remember it. And for a universe with different vacuum energy, none of that will matter at all. The new physics will not grieve. The new vacuum will not notice. The transition will be as indifferent as every other process in nature, caring nothing for what it destroys, because caring is not a thing that physics does. But we are not physics. We are the creatures that physics created, the configurations of matter that somehow became aware of themselves and their situation. And our caring matters, to us, for as long as we exist to care. The bubble cannot take that retroactively. It cannot reach back in time and make our caring meaningless. It can only prevent future caring, and the caring we have done, the love we have felt, the questions we have asked, all of that is real, was real, will have been real regardless of what happens next. This is not immortality. This is not continuation. This is not a way of cheating the bubble or escaping the danger. It is simply the recognition that meaning is not a function of duration. That value is not measured in years. That a life well lived is well lived whether it lasts a century or an instant. Whether it is remembered forever or forgotten immediately. The goodness of the good is not diminished by its ending. The truth of the true is not falsified by its destruction. These things are what they are, for as long as they are, and that is enough. It has to be enough, because it is all we have. And now, at last, we can return to where we began. To the night sky, vast and dark and filled with the light of stars that may not know they are metastable, that may not realize the Higgs field they inhabit is elevated, that burn their nuclear fires in a universe that is possibly temporary, possibly waiting, possibly already falling towards something else. They do not know these things because they cannot know them. They are not conscious. They are not aware. They are simply processes, nuclear fusion and gravitational collapse and electromagnetic radiation, going on as they have gone on for billions of years and will go on for billions more, or will stop in an instant without warning, depending on whether the bubble is real and where it is and how fast it is expanding. But we know, or at least we suspect. We have done the mathematics and examined the evidence and contemplated the implications. We have asked the questions that the universe cannot ask itself. And in that asking, we have done something remarkable. We have held the possibility of our own annihilation in our minds and not flinched. We have stared into the void and found, if not comfort, then at least clarity. We have learned that we are small and brief and contingent, and we have chosen to find in that smallness and briefness and contingency a reason for wonder rather than despair. This is what consciousness does. This is what it is for, if it is for anything at all. Not to guarantee survival, which it cannot, not to prevent catastrophe, which it cannot, but to witness, to understand, to make meaning out of matter and experience out of existence and something out of nothing, for as long as the nothing permits. The Higgs field stretches out beneath us, unseen and unfelt, doing its quiet work of giving mass to quarks and electrons, shaping the atoms that shape the molecules, that shape the cells, that shape the brains, that shape the thoughts, that shape the questions that brought us here, to this moment, to this contemplation of our own possible erasure. It does not know what it has created. It does not care. It is just a field, a set of values at every point in space-time, oscillating in ways that we have learned to describe with equations and probe with particle accelerators and worry about in the depths of the night when sleep will not come. And somewhere, perhaps, a bubble is expanding, or perhaps not. We will never know until it arrives, and when it arrives, we will not know at all. There will be no moment of realization, no flash of understanding, no last thought before the end. There will only be the world as it is, and then the world is something else, and the transition so fast that the speed of light itself is the harbinger and the destroyer at once. But right now, in this moment, the bubble is not here. Right now you are conscious, listening to these words, thinking these thoughts, existing in this universe that has somehow made room for your existence. Right now, the stars are burning and the galaxies are receding, and the cosmic microwave background is whispering its ancient story of the beginning of everything, and you are part of all of it. A tiny fragment of the universe that has become aware of itself and its precariousness and its wonder. This moment is all you have ever had. It is all anyone has ever had. The past is memory and the future is speculation, and the present is the only place where anything actually happens. The bubble, if it comes, will arrive in a present moment, but that present moment is not this one. This one is yours. This one is now. This one is the only piece of existence that you can touch directly, the only fragment of eternity that is actually yours to inhabit, and so we end where we began, with wonder, with the recognition that existence is strange and contingent and possibly temporary, and that these facts do not diminish its value but illuminate it. The false vacuum trembles beneath us, a foundation that might be forever or might be ending right now as these words travel from one mind to another. We cannot know. We cannot prepare. We can only continue doing what conscious beings have always done, asking questions, seeking answers, making meaning, loving each other, living our lives. The bubble may be out there, silent, invisible, racing toward us at the speed of the light, carrying the end of everything inside its expanding wall. Or it may not exist at all. We will never know which until we either know or don't, and if we don't, we will never have known at all. This is our situation. This is the universe we inhabit. This is the strange, contingent, beautiful, terrifying gift of consciousness in a cosmos that did not have to include it. Let the knowledge settle. Let it become part of how you see the world, not as a burden, but as a clarity. Let it remind you that the morning light is improbable, that the faces of the people you love are improbable, that the questions in your mind are improbable, that the very fact of asking those questions is a minor miracle in a universe that mostly consists of empty space and burning hydrogen. The false vacuum may decay, or it may hold. Either way, you were here. You existed. You asked the questions and contemplated the answers and felt, if only for a moment, the weight and wonder of being alive in a universe that permits life but does not promise it. And for now, that is enough. For now, that is everything. The night is deep and the stars are far and the fields that make us what we are silent and invisible and possibly unstable, waiting for a fluctuation that may never come. Sleep well if you can, and if you cannot, then watch the stars. They are still there, for now.